Hey everybody. So in this video, we're going to do the first intro for our chapter one, our unit one, and that's working with the real number set. So we're going to define and classify all the sets of real numbers and do some examples. And then afterwards, you will do a few of these types of problems on your own. So first thing we'll do is we will define these three sets. That's the natural, the whole, and the integer. And then right after that, we'll tackle the next two, the rational and the irrational. So let's start with the first of our number sets. And these allow us to classify special numbers into these different categories. So the first of them is our natural number. So natural numbers are, you think about, they get the name from nature. You think about the ways that you can count things that belong in nature. So these just mean these are counting numbers. So for your natural number set, the symbol is a capital N, and you'll sometimes see it with a double bar just so that it's very clear that you're referring to the set of natural numbers and not just some random capital N. So when we're talking about number sets or any set in general, we usually use our curly brackets. That's a bracket. And we identify that natural numbers start with 1. It's just how you count things. If I'm counting ducks on a pond, I would start with 1, 2, 3, and then we use the 3 dots, the ellipses, to imply that it goes on infinitely in that direction. So you'll see that the natural, which are our counting numbers, is the first of our sets. Then we branch out a little bit to the whole number set. And the whole number set, what makes this different, there's only one thing that makes it different from our natural number, and that is the 0. So the whole numbers start at 0, so it includes 0, and then all of these other positive integers, 1, 2, 3, 4, 5, 6, 7, dot, 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 implies it goes on infinitely in that direction. So we've got natural and we've got whole. And underneath here, I'm going to show you a Venn diagram. And this tells us that every number that is a natural number is by default going to be a whole number too. Let's go to our third of these number sets, and that is the integer set. And that is a capital Z. And it gets its Z from the German word for number, which is Zahl. And that gives, by definition, your integers. These are still whole numbers, but they take on both positive and negative values. So I'm going to write this one here. So you'll notice for this, the ellipses start on the left side as well, meaning it goes on infinitely to the left if we're thinking about our real number line, and then it will go on infinitely to our right. So we could do -4, -3, and we're including all of those numbers, 1, 2, 3, 4, and then again 5, I'll throw in a 5, dot, 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 to show that it goes on infinitely to the right as well. And on our Venn diagram, I'm going to run out of space. We're illustrating that the integers are sort of the larger set, and within it, integers will contain every whole number. And in that, it will contain every natural number. So if it's a natural number, it's a whole number. If it's a natural number, it's an integer. Okay, now that takes us to the next two, and that is rational and irrational. Let's start with rational. So the symbol for rational is actually a Q for quotient. And when you think quotient, I hope you think that looks like division, right? Sometimes a fraction. So we define a rational number as any number that can be written as a quotient or a ratio of two integers, any two integers you want. So let's throw in some examples like negative 17 over 4, 5 over 1, negative 29 over 29. These are all examples of what rational numbers look like. As long as I have an integer on the top and on the bottom, and you'll notice this one we could have written as 5, right? Because those are both the same expression. But I can write 5 as 5 over 1, so it satisfies that definition of a rational number. Now, not every number is written in that fraction form. What if it's written as a decimal? So then it's in disguise. So let's take on sort of the decimal definition of a rational number. So any decimal that terminates or repeats, I'm going to put here ends. So a decimal that has an end, meaning 2.73. Right? So 2.73, there's a hard stop after 3. So this would satisfy our definition of a rational number. So that would be an example of a decimal that ends, that terminates. Now let's talk about those repeating decimals. You might see 0.26. Have you seen these where it's 26 repeating? That would be an example of a decimal that repeats. Negative 1.3333. That would be an example of a decimal that repeats. So that then satisfies our definition for rational numbers in terms of our ratio of two integers versus our decimal. So then we've got the last of those. Oh, let's put the Q where the Q belongs. So our rational number, I've got my Venn diagram, would be here. What's that mean? That means if a number is a natural number, it's a rational number. If a number is a whole number, it's a rational. If a number is an integer, it's a rational number. So then that takes us to this loner, and that is irrational. So we're going to abbreviate that with an I. Irrational numbers are the opposite of rational numbers. So that just means if I can write a number as a quotient of two integers, it's rational. If I can't write that number as a quotient of two integers, it's irrational. So we define that by saying it can't be written as a simple fraction. What do you think your decimal definition is? Our decimal approximation, or our decimal definition, is one that is non-terminating or non-repeating. So a decimal that doesn't end, but it also doesn't repeat. What numbers can you think of that would fit that bill? Here's our famous one, pi. So you're 3.1415, and there's no pattern, there's no repetition, but it goes on infinitely without repetition. So the others that you'll see are the radicals, and we'll get into radicals in greater detail later, that aren't perfect squares. Root 2, root 7, negative root 3 are examples of irrational numbers. And I'm going to make this messy, but I want you to be mindful of the fact that all of these, both rational and irrational, fall under the realm of the real number set. And I'm going to give you a diagram that looks a little neater. So you'll notice here, this is a tidier Venn diagram of what we just covered. And you'll notice here are just a few of many, infinitely many different examples of numbers that fall under specific sets. So I'm going to actually erase 0 for a second. But if we were to try to classify 3, and we said, well, what set of numbers does 3 belong to? We would identify that 3 belongs to the natural numbers because it satisfies that definition. 1, 2, 3. It's a counting number. And by default, if it's a natural number, it's already embraced in the whole number system. It belongs there. It's already embraced in the integer system. It belongs there because the set of integers includes natural numbers. And then it's also included as a rational number, which then makes it a real. So it would fall under all of those categories. So it looks like this. If this is our real number set, then reals either branch out to rational and irrational. Irrationals are the loners. They've got no friends, right? But here, for our rational numbers, I know that those contain subsets of integers, wholes, and naturals. All that to say is that means if a number is a natural number, it follows this choo-choo train, meaning, well, then that means it's going to be a whole number, it's going to be an integer, it's going to be a rational number, which makes it a real number. Let's do a few example problems. So here is a question that's asking us to categorize these numbers in terms of the sets that they belong to. So why don't we start with negative 0.5. So I would work my way down. So let's identify. Negative 0.5 is for sure a real number. Every number that we're working with to date is going to be a real number. We'll talk about what the other set is later. So it's definitely a real number. Then we need to figure out, is it irrational or is it rational? Well, it's a decimal for sure, but it terminates. It's a decimal that ends. That makes it a rational number. Then we go to C, just going along in our sort of, I'm going to arrow it so it's clear. So if I'm working my way down, next step is it an integer? And since we have a decimal, remember, integers are positive and negative whole numbers and 0. It's not an integer. So that's the only solution that we have for negative 0.5. I might pause this and try to do the rest of them on your own and see if you end up with the same results. So negative 1 is a real number. It's not even a decimal, so that makes it rational. And from there, let's continue. Is it an integer? Well, yes, because it's a negative whole number. So I know it's an integer. Well, is it a whole number? Remember, whole numbers start at 0. No. Oh, I meant to just do 1z for clarity's sake, at least, so it doesn't look so confusing. Good. So we keep going. We've got this real number, negative 3 over 4. It is written as the ratio of two integers. It makes it rational. Then I go to the fact that, is it an integer? No, because it is a fraction. So I can nix that comma because those are the two sets it belongs to. So we definitely have a real that is not irrational, so it's a rational number. Can be written as 0 over 1. Is it an integer? Sure enough, it's an integer. So then we go down to the next set, which is whole. Is it a whole number? Yep, it's the first of our whole numbers, the smallest one. And then that takes us to natural. Well, 0 is the only number in the whole number system that is not natural. So we leave our 0 like so. Oh, and now we're on to root 50. That's a good one. Root 50 is not, so let's just look at 50 first. Since 50 is not a perfect square, it's not a perfect square, that would make this radical definitely real, but irrational. That's going to give us a decimal that is non-terminating and non-repeating. All right, 0.8. We've got a decimal that ends, that makes it a rational number. And then we're on to the integer question, which it's not. Get rid of my comma. And here, this question is meant to, because of the ellipses at the end, meant to imply that it goes on and on. So this is a decimal that repeats. So this is a real number. It is definitely rational because it is a repeating decimal. And it is not an integer because it is not a whole number. So we're left with real and rational. And then our last example is 2, which we know is real. And I'm hoping by now we know that's rational. Is it an integer? Sure is. Is it a whole number? Yes, it falls under that whole number set. And it's natural because it is a counting number. And we made